Hi everyone, I'm Huan from Central University of Finance and Economics in China, supervised by Professor Lixin. It's really a pleasure for me to introduce our work to you here, which is titled LGL-GNN, Learning Global and Local Information for Graph Neural Network. Next, I will introduce our work from 5 parts. At the beginning, let me introduce the background of our work. Graph can flexibly describe the complex relationships between real things and has a strong structured expression ability. However, unlike image data with a regular grid structure, each node in the graph has a different number of neighbor nodes. So basic convolution and pooling operations cannot be used. Therefore, researchers try their best to extend CNN to the graph, which develop a novel field named graph neural network. There are two strategies used for design of graph convolution operation. The first is spectral-based and the second is spatial-based. Spectral-based GCN is usually used for vertex classification tasks, and spatial-based GCN is good at handling graph classification tasks. But in actual situations, the particularity of graph structure brings some problems to GCN. One of the most difficult problems is oversmoothing. As the number of network layers increases and the number of iterations increases, the representation of each node tends to converge to the same value, which means that the global information of the entire graph will be synchronized to each node instead of the local structure features we expect. To overcome the problem of oversmoothing, there are roughly two ways of thinking at present. Now, let me show you the related works about it. One way is using sort pooling layer to replace sum pooling. For example, Zhang Muhan proposed a novel deep graph convolutional neural network, DGCNN, which used a novel sort pooling layer to sort the extracted multi-scale vertex features instead of summing. The other way is convolving the local subgraph of the node. For instance, Zhang Zhihong designed a local convolution operation based on a subtree. The core ideas and convolution formula of these two models can be seen in the second part of our paper. Although both methods alleviate the oversmoothing to a certain extent, the former may lose the feature of some vertex, while the latter may lose global information. So we proposed the LGL model, inspired by the simultaneous attention and fusion of global and local information. Now, let's have a look at the model proposed by our team, which is the most important part of our paper. As shown in the figure, this is the overall framework of our LGL model, which is a novel hybrid convolution structure based on GCN and SCN. GCN is based on the one-hop neighbor propagation of the node, including the global topological characteristic of the graph, and each node in SCN only aggregate adjacent motif neighbors, representing the local node information of graph. We use GCN and SCN to perform 3-layer convolution on graph respectively, and splice the convolved feature as shown in the figure. Then, the spliced features are sorted into a grid structure, which can be directly subjected to one-dimensional convolution. The specific hybrid convolution formula is on page 5 of the paper. What's more, we designed a new local convolution operation based on motif in SCN. Motif is a subgraph that appears frequently in graph. Each node in motif has strong connectivity. Thus, the using of our motif-based SCN can effectively capture high-quality local neighborhood information. In order to better learn the strong connection relationship between nodes, we introduced motif and designed SCN based on motif. Specifically, SCN includes 4 key steps as shown in the figure. First, rank nodes according to their degree. Second, find neighbors based on motif for each node. Third, construct a M-array tree for each node. Fourth, arrange the tree into a regular grid structure. A more detailed operation diagram can be viewed in Figure 3 in the paper. Regarding GCN, we use the convolution formula proposed by Huan, which can be seen in the second part of our paper. At last, the attention mechanics give weight to the global information GCN learned and the local information SCN learned. So, how does the model work? Here are the experimental results. We set up the experiments on benchmark datasets to evaluate the solid performance of the proposed LGL model against both state-of-the-art graph kernels and other deep learning methods on graph classification problems. In our evaluation, we adjust a number of hyperparameters to get the best performance of each dataset, as shown in Table 3 in our paper. In SCN, we set up 2 motifs, triangle and 4 cycle, to capture the neighbors of nodes, and construct 2 array and 3 array trees, respectively. For our model, we perform 10-fold cross-validation to compute the classification accuracy, with 9 training floats and 1 validating float. For each dataset, we repeat the experiment 10 times and report the average classification accuracy and standard errors in Table 2. We can see our LGL model can significantly work better than these baseline methods, and we have summarized 3 reasons for this. Firstly, as mentioned earlier, most deep learning methods for graph classification cannot well avoid the problems of oversmoothing and retention of rich global and local information. But our LGL can alleviate these problems and get better representation learning. Secondly, our LGL model can provide an end-to-end deep learning architectures. Last but not least, the use of motif to extract strongly connected neighbor information for nodes simplify the steps of quantum work in QSCNNs. The splicing of the results of local subgraph convolution and deep graph convolution has achieved a performance exceeding the GNN. This empirically proves the effectiveness of our LGL model. Finally, in conclusion, we have shown how to construct a motif-based subgraph convolution network for a graph and how to make use of both the global topological arrangement information and the local connectivity structures within a graph. Experimental results on graph classification show our LGL model is superior to a number of baseline methods. It's interesting to notice that different practical problems have different requirements for global and local information. For example, social networks may rely more on the near-end neighbors of nodes, but the properties of chemical molecules may depend on some remote nodes. In addition, the choice of motif also greatly affects the effect of graph classification. Our future plan is to explore the impact of more types of motifs on the experimental results and a better way to gather global and local information. That's all. Thank you for your attention.